Okay, so I've got a just quick video for you. This is related to one of the problems that's on the second optimization problem set. So the reason this is on there, it's because it's a problem where you're having to calculate a cost and a cost of producing this, this capsule-shaped industrial pressure tank, and the hemispherical ends cost twice as much per square foot of surface area as the cylindrical sides do. Okay, so that's a good calculus question where you could think of it as you're weighting the areas, the surface areas differently on the different parts of the shape. So we're supposed to minimize cost here, okay? We've got a picture, we need to define some variables. What if we said something like the radius of both shapes, we'll call R. Oh man. Okay, so we'll call the radius of both R. We could call the length of the cylinder, let's just call that X. So the distance from there over to there. And a couple things we might want to remind ourselves about. We know that the volume of a sphere is 4/3 pi r cubed. Surface area of a sphere 4 pi r squared. The volume of a right circular cylinder is pi r squared h. But in this case, h is x, so pi r squared x. And the lateral surface area, just the surface of the barrel part of that cylinder, is going to be 2 pi r times h, which in this case is x. Okay? So what pieces of surface do we need to build this shape? Well, we have two hemispheres combined. That's equivalent to one sphere, and then I've just got the lateral surface area of the cylinder. So how are we going to set up our cost function then? We're going to minimize cost. So our cost function, we're going to have the lateral surface area of the cylinder, which is 2 pi rx, plus we've got the two hemispheres combined, which is a complete sphere, and the surface area of that is 4 pi r squared. But how do we account for the fact that the hemispherical ends cost twice as much per square foot of surface area as the cylindrical sides? Okay, well, we don't know how much either one of them costs, but we could just say arbitrarily, let's say that the cylindrical sides cost K, right? So then we're multiplying this cost per unit area, K, times the surface area, and combined, that's giving us the cost of the cylindrical sides. And we could just even define over here, K equals cost per unit area for the cylinder. Okay. Well, then what would the cost per unit area for the hemispherical ends have to be? If they cost twice as much, it's just 2K. So there you go. So there's our cost function. Problem arises here because I've got two variables, but I have a constraint. We know that the volume of this tank has to be 4,000 cubic feet. So the volume we know is going to be the combined volume of the cylinder and a sphere, because we get two hemispheres. So what's that going to look like? We get 4/3 pi r cubed plus pi r squared x is equal to 4,000. So there's an equation, secondary equation we can use to solve for a variable and substitute. Well, it looks pretty clearly like the one that we want to substitute for is x, because x only shows up once to the first power in each of those two equations. So if I solve for x in my equation of constraint here, I'm going to get, let's see, what am I going to get here? Let's do it in two steps. So pi r squared x equals 4,000 minus 4/3 pi r cubed. Let's go ahead and just clear all the fractions by distributing a 3 through the whole thing. So we just get rid of that 3 on the bottom. So that's going to give us 3 pi r squared x equals 12,000 minus 4 pi r cubed. Now we can divide each side through by 3 pi r squared.